All right, so we throw a ball into the air, and we want to know at what point the force on the ball is equal to 0. So let's be clear. Here I've got gravity. Here I've got gravity. Here I've got gravity. Even though it stops for a quick second in the vertical direction, gravity still pulls it back downwards, which is why it's able to continue to fall. So what that actually means is there's always gravity acting on the ball. No. An object is placed on a planet where the acceleration due to gravity is twice that of Earth, so that means it's going to be 20 meters per second squared. That's going to be the new g value. So we want to know the weight on this planet. So weight, instead of being mg, it's going to actually be, we're going to use the new g. So instead of weight being 10 times m, normally, our new weight is going to actually be 20 times m, so twice as much weight. Here. F1 is the force exerted by Earth on a tiny little fly. F2 is the magnitude of the force exerted by a little fly on Earth. This is absolutely our standard third law problem. These forces are equal. And then for 18, we want to know what the free body diagram of the shopping cart looks like, and we know that there's some friction acting on this since it's moving at steady speed. So we're going to have the normal, we're going to have the weight. I have the pushing force down on the cart at this angle theta, and I have a force of friction on the cart. So it looks like choice D is the best answer. Now, what is the total combined force on this cart equal to? How do we know? Well, the cart is moving, so that's not right. Non-zero in the horizontal? Well, that can't be right since we're moving at a constant velocity in a straight line. So we definitely have zero force, net force acting. It is possible to determine it. We may not know what the exact number is for the speed, but we do know what the combined force is equal. So in the horizontal direction, we're actually at 0 because the cart moves at a steady velocity. In the vertical direction, we're 0 because we don't fly up into the air. That leaves us choice B, because that said non-zero, which isn't right. And then for number 20, a giant fly of mass 0.01 is thrown against a 4,000 kilogram truck at a speed of 20 meters per second. So the fly hits and stops, and then we want to know what speed the truck goes after the fly hits it. You might guess 20 meters per second. Why would a fly affect the truck? But let's actually calculate this out. So let's get the acceleration of the fly. So I know that I can use v equals at plus v naught for the fly. So that's going to be v is 0 equals a times 0.02 plus 20. And so my acceleration is going to be negative 20 over 0.02. That's going to be 2,000 divided by 2, which is going to end up being negative 1,000 meters per second squared. Now the acceleration then is going to be negative 1,000. Now let's get the force on the fly. That's going to be, F on the fly is going to be m times a, which is going to be 0.001 times negative 1,000. And so that's going to give me negative 1 meters per second squared. Now let's figure out what happens to the truck. Since the force, sorry, that's not negative 1 meters per second, that's negative 1 newtons. Let's figure out what the force on the truck is now. Well, by Newton's third law, that's going to be 1 newton on the truck, by Newton's third law. Let's get the acceleration of the truck. 1 newton is going to be 4,000 times a, so I'm getting 1 over 4,000 for my acceleration, which ends up being like 0.00025. We can go ahead and plug this in. We can say, like, what's the final speed? V equals at. We could try that, like, v equals at plus v naught. So 20 equals 0.00025 times 0.2 plus v naught. But let's face it, we know we're going to get 20 meters per second squared when you plug in that tiny number. So basically, the fly is not able to affect the truck, which is exactly what we would expect. So that's it for the multiple choice section, and in the next videos, we'll take a look at the free response problems.